Okay, welcome everybody to today's special webinar seminar. Uh, Today we are very happy to have Rohan Pramanick, who is a postdoc at ISS, University of Cultivation Sciences in Kolkata. So Rohan did his PhD from IIT Kharagpur, working on various topics on dark matter detection, and also dark matter model building, and his first postdoc. And today he'll be talking to us about his work on generation of how to make visible and dark matter in the vanilla scotogenic model during the peak work, apart from like some.
Thank you for the kind introduction. Of course, Scotogenic is a Greek word, where scoto means dark. So it is something to do with dark matter built in the. So let me start with the field condition standard model. So this is the standard model where there are these quarks, there are leptons, and there are various gauge bosons mediating sort of three fundamental forces of nature, namely the strong, weak, and electromagnetism. And this is a very nice cartoon which encompasses all the ingredients that you can have, uh, from the content of the quarks to the SU2 interactions to all the gauge boson interactions that are present in the standard model, which I took from the quantum magazine. And this is the description of standard model, which sort of gives a quantum description of these three fundamental forces of nature, taking gravity into account. So, the standard model, we start with the idle fundamentals. After the heat of potential is there, it can give rise to the mass of the atoms and also the gauge bosons by something which is written over here. It's the power interaction, and when this Higgs gets a vacuum excitation value, you can write down a Dirac-like mass term for the atoms, which is proportional to the wave of the Higgs and the U power. But you see that for to write down a Dirac-like mass term, you need to have both the right-handed and the left-handed counterpart of the formula. And due to the absence of this right-handed counterpart of the neutrinos in the standard model, as you can see that the neutral component here, there is no neutral part over here. There is the right-handed sector, and there is no neutral part. So as you can see in this cartoon, there is no Dirac-like mass term for the neutrinos in the standard, and neutrinos are massless. But we have certain observational evidences that suggest neutrinos should have some tiny but non-zero mass, and we have confirmed with neutrino oscillation experiments where neutrinos can change their flavor during propagation. That is, an electron neutrino while propagating can change its flavor to a muon neutrino or a tau neutrino with some finite probability, which if you want to give an analytical description, you need to have some kind of non-zero mass, as written over here, that this P is proportional to this mod m square. Now, delta m square. This delta m square is nothing but the difference of difference of masses of different flavors, and this has to be non-zero. So we have this evidence of neutrino oscillation, which suggests that neutrinos should have some non-zero mass, but as you have seen earlier, they remain massless within the context of standard model, which is one of the motivations to do physics beyond standard model. Now, you can incorporate neutrino mass within the context of standard model only by the same mechanism of by the same mechanism of electric symmetry weighting. You just have to add 3 copies of right-handed neutrinos, and you can say that the neutrinos obtain their mass in a similar fashion like other tidal fermions do. But in that case, you have to find the U-power coupling so much that you obtain this kind of number, a to the power minus 13, to obtain this kind of neutrino mass, which is at the sub-GeV scale. So this requires a lot of fine tuning, and we seek to get some answer from the neutrinos, but this kind of fine tuning is not present. And fortunately, because the neutrino is electrically neutral, present, you can devise those kind of techniques by which you can give neutrino mass other than the electricity. We'll talk about this kind of mechanism in a bit. But moving on, you also have this kind of baryon asymmetry in our universe. That at a cosmological scale, you have only baryons, or let's say matter, and there is very trace amount of antimatter present in between the cosmic rays and all those kind of things. But mostly those are made of matter, and we see there is very tiny amount of antimatter present, and this sort of asymmetry between the matter and antimatter cannot be explained within the context of standard model, because if you want to dynamically generate any kind of asymmetry within the context of standard model or the gauge group, you need to satisfy these conditions, which are namely the Sakharov conditions, which say you need to satisfy this condition, which is you need to violate radial and lepton number, which we know are accidental symmetries in the standard model, and they are preserved or more precise with the combination of P minus L is anomaly free, and that is respected within the context of it is a global symmetry. Then you also need to have CLCP violating processes, which is present in the standard model weak sector, but the amount is not enough to explain the observed symmetry of the universe, and it is also required that these processes of CLCP violating processes should go out of equilibrium, so you retain some kind of net asymmetry within the universe, so that it can evolve and give rise to a visible and dark sector. So there is no explanation of baryon asymmetry of the universe within the context of standard model. Now, in order to tackle both these issues, people have already devised models of neutrino mass which can address both these issues simultaneously. So these are known as neutrino mass models. And in order to explain both these issues within the standard model, we need to incorporate higher dimensional terms. Um, uh, and if you go beyond the four-dimensional renormalizable countings, you can actually uh, show that by including only the high-dimensional operator, you can explain both these issues. So this is that there is only one and only one operator that is known as the Weinberg operator, which includes two electron doublets and two Higgs doublets. So if you expand this operator, you can have various realizations, and in order to explain these two issues, you have to impose one additional mass scale, which is known as the seesaw scale, which is kind of very heavy. And this word seesaw comes from the fact that the neutral mass is inversely proportional to the seesaw scale. So as the seesaw scale becomes large, neutrino masses are small, and there the name comes from the seesaw names comes from there. So if you open up the Weinberg operator, you can have three possible realizations at the tree level. These are known as the type 1, type 2, and type 3 seesaw, where you extend the standard model by either extending the fermion sector or by extending the scalar sector. So in type 1 scenario, you extend the fermion content of the standard model by three massive right-handed neutrinos. In the type 2 seesaw, you extend the scalar sector of the standard model by additional scalar triplets, and this type 3 is kind of similar to the type 1, where you extend the fermion sector of the standard model by fermionic triplets.
Technically speaking, the criterion need not be very heavy. It can be accessible colliders.
It can be accessible in colliders, but then you have Yukawa couplings that are fine-tuned to this model. Okay. So these seesaw models are designed in a way that they can address the finite neutrino mass and can also explain the baryon asymmetry of the universe if you have certain ingredients, but it cannot explain the another mystery of the standard model, namely the dark matter, which we know that there exists some kind of non-luminous content of our universe, which interacts only gravitational until now, and so this picture is not correct. Okay. So, and we have various evidences for dark matter, namely the galaxy rotation curves in the cluster gravitational length and all those. It has to satisfy certain conditions, and it is roughly 25% of the energy budget of our universe. We do not know much about dark matter. Mainly the particle content of the particular nature of dark matter is also not known. But people have written models where the mass of the dark matter can span a large range. So in order to address three of these problems, one can also look for realizations of the Weinberg non-trivial. So the most simplest radiative model, that is neutrino mass model, where the neutrino mass is generated from loops, one can write down, is written by Ernst Mach, and this is known as the Scotogenic model. So what one does is that one extend the scalar sector of the standard model by one SU2 doublet scalar field, which is written over as eta, and three right-handed neutrinos N1, N2, and N3. And in order to stabilize the dark sector, or let's say in order to get a stable dark matter candidate, all these exotic species are all under Z2, and this Z2 is intact, so that the dark matter does not lose its stability. So with this field content, one can write down a similar Lagrangian like the type 1 seesaw, where there is a Yukawa term. This is y, l, eta, and ni. So this is the scalar doublet, and this is the fermionic singlet ni, and this is the mass of the right-handed neutrinos. And you can also write down a potential for this model, where there is the usual standard model Higgs, and there is this additional SU2 doublet scalar, and you can write those various terms, but you need to make sure that the Z2 is preserved. So you choose your mass term with the correct sign, that is L meter square mass. So that is the only requirement that you need to have while writing down this potential. And if you write down all these couplings, you can generate neutrino masses at the loop order. And this diagram is given over here, where in the loop there exist particles which are all under Z2, and this is the famous Weinberg operator, where there are two leptons in the external side and two Higgs states are there, so the neutrinos are massive after the electrons. So if you calculate this, you will end up with a loop function which involves the mass of this exotic scalar and this fermion. And if you kind of massage a little bit, you will find that this loop actually is non-zero if there is a tiny mass splitting between this real and imaginary part of the neutral component of the scalar that you have. And that mass splitting is directly proportional to this lambda 5 coupling, which is the only coupling that sits in front of this non-self-efficient coupling, and this has to be non-zero in order to produce non-zero neutrinos. Otherwise, this is direct. So with this neutrino mass, one can also look for how the baryon estimates of the universe can be generated from this. And this has also been addressed in the literature.
Oh, so the lambda 4 and lambda 5 are different.
Yes, so this lambda 3 and lambda 4 are kind of different type of contractions that you can have between
lambda 4.
So lambda 5 is this age diagram, and lambda 4 is the Hermitian. Okay, so
Can I ask one question? This I always have this, sorry, completely beyond your talk. So when people talk about this Scotogenic model, I know they introduce all these scalars. And I know you're not address it. Have you ever seen people talking about what happens to the hierarchy formulation? Like you're introducing scalars like randomly.
Yes. Okay. So I have not looked at the hierarchy of this. So there are so if you have this kind of adding scalar will decrease the stability, right? But then you have this right-handed neutrinos that can stabilize the potential. So
that is the potential. But also the fact that you're adding scalars. I mean, why are the scalars not at the cut scale? The same problem as the
yes, so you can choose this scalars at the cut scale. There is no kind of symmetry protecting it, but it has some issue with this decay problem that. So there are some issues with this choosing the mass of the eta to the cut scale, which will give rise to this problem. Okay, thanks. Okay. So for leptogenesis, one needs to the first starting point of the leptogenesis is to dynamically create an estimate from a decaying particle. So here the right-handed neutrinos can be heavier, and it can decay into a lepton and the scalar doublet. And the asymmetry parameter that has been written over here can be quantified as this. So it is the difference of the decay width of a right-handed neutrino going to a particle between going to an antiparticle. So here I missed. So here I missed this part. So there will be a part. So this right-handed neutrino being a Majorana particle can decay to L eta. Also, it can decay to an L bar eta bar. And the difference between these two decay rates will give rise to asymmetry, which has been quantified like this. So this asymmetry will, if you want to calculate the asymmetry, you want to take care of the tree and the loop level diagram for this right-handed neutrino. And the interference term that you have from this tree and loop level will give rise to this non-zero epsilon. And this expression is written over here, but this H is the loop. Now, before proceeding to solve this,
maybe asymmetry in the period, can you tune CD violation in the cortex side?
yeah.
Yes.
So even if you have, let's say if you omit these two diagrams, if you have a complex power coupling, right? So it will not create any asymmetry because this gamma will be mod square. So this mod square will kill off the image. Then you need to take this both these two. Okay. So with this non-zero epsilon or this non-zero asymmetry parameter, you can proceed to solve Boltzmann equations for this abundance of this lepton. But before going into this, I will give a brief review of what this kind of Boltzmann equation does in a kind of numerical way. So I will introduce this a toy scenario of freezing, where let's say you have three fields, phi 1, phi 2, and phi 3, and you have only this kind of Lagrange interaction Lagrangian to play with, where this mu is the dimension full count. And if you were to write down the Boltzmann equations for this phi 1, phi 2, and phi 3, these three are the Boltzmann equations. You see, if this is a very simple scenario, so this y2 and y3, which is the decay product of 1, follows the same Boltzmann equation.
So why is this condition required, which is M1 is much greater than M2 and M3?
So in order to if phi 1 has to decay into phi 2 and phi 3, this is the diagram that at rest it has to be. Okay. So this is the Boltzmann equation where this dot represents this quantity. This is nothing but the change of abundance. This small y is nothing but the scale abundance, and this abundance is actually defined in terms of co-moving number density, which is defined as a number density per unit information. So this is the Boltzmann equation for y1, y2, and y3, and there is the only difference between y1 and y2 is that there is a minus sign. This is more like a equation of which you encounter in the decay, or let's say radioactive decay, where the decay rate is usually proportional to the substance that you have. So that is the Boltzmann equation for y1, and the decay product, that is 5 2 and 5 3, can also recombine to give y1, and this is happening in a sort of expanding universe. So you need to also take care of those. So there comes this Hubble parameter, and you need to subtract this forward reaction from this backward reaction and multiply with this gamma, which is nothing but the reaction density, which tells you how strong the decay, or let's say how strong the process is compared to the expansion of the universe. And you get, if you solve these three equations simultaneously, you get this Boring plot, in the sense that if you start with let's say 10 to the power minus 2 amount of y, because there is a number conservation, you ensure that your phi 2 and phi 3 is also the same as you start. So this kind of boring, but what people usually do is that they neglect this term. They neglect this term during this kind of calculation, just with the back of the mind approximation that this is much more negligible numerically, but this is not true, because let's say if you arbitrarily rescale this back reaction a little bit, you will end up having different abundances for y2 and y3, which is kind of not correct. But people usually do this, but this is the actual solution that you get if you solve it.
So what is this back reaction?
So this y2 so this term minus y2 and y3 kind of tells you that the decay products y2 and y3 will sometime back react to give you phi 1. And in this kind of setup, people actually, in many literature, you will see that this 5 and 5 abundance has been carried out without writing this 5 1. But my point is that if you actually want to solve it correctly, you need to put this y2 and y3, because if you rescale this arbitrarily, let's say if you put b2 and b3 to 0, you will end up having different amounts of phi2 and phi3. But that is incorrect, because there is always a number on the direction. If you let's say start with 100 phi1s, you will end up 100 phi2 and 100 phi3s, because there is a number conservation built in the structure.
Okay, so so but why can't so you're saying so okay, so first equation is first part is obvious. Y1 is just decaying to M2 and M3, but then M2 and M3 is recombined to produce Y1. That's
Yes.
just, I'm sorry, M1.
Yes.
But so that reaction means it's also competing with Hubble, right?
Yes.
Yes. So and that is built into gamma.
No, this gamma actually takes the strength of, let's say, 550,
Yes.
and this gamma should be multiplied with this one and this one also, because there is
Yes.
so but people usually
So that
drop this.
It is happening in expanding groups.
Yes, I think the moment.
Yes. Okay. That will. Okay.
So this will you take the direct y.
Yes.
Move it.
So I think what you mentioned about the back reaction thing. So this is so am I correct that
Yes, it's confused in the back reaction that depends on because that the y2 plus y3 going to sorry m2 plus m3 going to m1. So that depends on the Hubble expansion. Also. It's competing with the Hubble.
yes, so that kind of depends.
Yes.
But I mean, this gamma is the strength of the process,
Yes.
but it doesn't tell you what is the rate of reaction, what is the forward and this is the rate of the process. But these numbers actually quantify how they are. So the correct way to solve is that y1 minus y2 by 3, but people sometimes drop these two terms because they are numerically insignificant.
This boom.
This is cool.
One other thing. So you're writing that as B2 and B3 separately. Why can't you just write just B for both?
Yes. So I have just written down B2 and B3 just to mimic the fact, because if you write B2 and B3 different, you will end up having different documents. It is just a toy scenario to kind of motivate that these back reactions are important in the sense that they should be taken into the Boltzmann equation.
So that reaction is when phi2 and phi3 are going back to phi.
Fine.
So in that sense, B2 and B3 aren't they always same?
So in this simple model, B2 and B3 are same. But this is a toy kind of scenario because we will encounter some, let's say, more complicated Boltzmann equations where there are additional processes, let's say, other decay modes, other branching ratios, many kind of scattering processes, which will kind of simulate this. That's why I have taken different pieces. This is just a toy, just to motivate what back reaction is.
And there is an inflection point there. I mean,
Yes.
yeah.
So yes. So what happens is that, let's say, phi1 decays. Now, as phi1 decays, phi2 and phi3 is produced. Now, at some point of time, this decay, the forward reaction, the backward reaction starts to dominate over the forward reaction, and then you produce more y2 y3, and this kind of back reacts to give you phi1.
Even in absence of B2,
Mhm.
there are inflection points.
Yeah. So this kind of depends on the strength of this mu. So if you take a stronger topic, you will not have this inflection point, but it will drop rapidly. But if you take mu to be small enough, this decay will be very slow because it will compete with the expansion of the universe, and this decay will be kind of flat. So this flatness depends on the strength of this, the strength of the decay of I1 going. What are those given and given? So these are Bessel functions that arise due to the evolution of the universe, because we are dealing these processes in kind of background metric. That is this. Okay. Also, if you have multiple decay channels, then you will end up having abundances which are less compared to what you started. So this is also a toy kind of scenario, which I have mimicked by writing C2 and C3. And if you take C2 and C3 to be, let's say, not equals to 1, you will end up having less number of phi 2 and phi 3. That indicates that there are additional channels of phi 1 which I have not written up in this simple toy scenario. Phi 1, some part of the phi 1 goes to that kind of processes, thereby decreasing its number, and you end up having less amount of it. So this is kind of the toy scenario of what is going to happen. Now let's come back to it. So how we achieve this kind of cogenesis scenario in this photogenic model. So the idea is this, and this is the relevant Boltzmann equation. These are some schematic pictures, but the idea is essentially this. So you have a primordial bar where you have heavy neutrinos, like let's say heavy right-handed neutrinos. And we have chosen a mass hierarchy. Let's say M3, that is the mass of the third right-handed neutrino is heavier than the second, but the second right-handed neutrino is heavier than the eta particle, that is the scalar doublet, and the dark matter, that is the N1, is the lightest. So we have taken this hierarchical scenario where M3 is greater than M2, M2 is greater than M eta, and M eta is greater than M1. So the idea is this: you have a primordial bar, and the primordial bar consists of this dark state A2. It is in thermal contact with the primordial bar. It has a CP violating decay, the one I showed earlier. It decays into a lepton and an eta, and this CP violating decay will produce some kind of extra L, or let's say some kind of extra leptons, which will create this lepton asymmetry. And this lepton asymmetry will undergo this Faraday conversion, where it will become atoms and will populate the universe with the physical. So from this CP violating decay of EU, you get visible matter from this side. Now you also generate some kind of asymmetry in the scalar sector, that is eta. You generate some tiny asymmetry between eta and eta bar, but this eta and eta bar decays dominantly into N1 and lepton. But this decay is CP conservative, so this decay will not create any kind of extra asymmetry between this extra asymmetry in the lepton sector, but it will produce many N1s. So this is a straightforward CP conservative.
So by primordial path, you mean after inflation, these things are produced by VGT?
Yes. So before inflation, here we are not interested because it will erase it. Okay. So the deep
And N3 is too heavy.
N3 is also too heavy.
Yes,
You
right.
can take into account everything, but it will eventually dominate. Okay. So eta will decay directly into N1, creating this dark sector, but it will also have a thermal contact with the primordial soup by this kind of processes, that eta and eta bar will go into Higgs and Higgs bar dominantly, and there is a transfer of asymmetry between the eta and lepton sector by these kind of processes, where eta L goes to eta bar. So this is the main idea of how you can generate both the dark sector and the both the dark matter and the lepton asymmetry, which undergoes Spellman conversion into this final baryon asymmetry in this kind of Scotogenic setup. Now, to write down to quantify the numbers, you need to track the abundance for 5 species, namely this N2. Then you need to track the abundance of eta, and because eta is not a self-conjugate particle, you need to track two versions of eta, that is the symmetric part of eta and the asymmetric part of eta. So there is eta plus eta bar and eta minus eta bar. Because eta is not a self-conjugate particle, you need to track this. And here what I have written down schematically the abundances of the asymmetry of lepton, and this is the abundance for the lightest right-handed neutrino, which will serve as stable diameter. So here you can see that the CP violating decay will introduce a non-zero asymmetry parameter, which is rising. This one over here, this is epsilon 2, that is the asymmetry parameter generated from the decay of N2, and this acts as a source star to generate this asymmetry. Now, once you have this kind of non-zero number, you can evolve this asymmetry up until this point, and this equation, this Boltzmann equation for delta one step, where you have, let's say, scattering processes like eta going to L bar L bar, and these kind of processes are also there, which will transfer the asymmetry between here and here. If you want to write down the Boltzmann equation for the stable dark matter candidate, you also have this Boltzmann equation where the dominant part comes from this decay of eta, where eta directly decays into a lepton and a dark matter candidate. So this is kind of the source term, and there are various other processes.
So this last eta goes to L by L. So there is no eta goes to L. Is that possible?
Eta goes to L will violate. That is a okay. So there are these scattering diagrams that I have written schematically over here. Now we have changed the three parameters of this model, namely the Yukawa couplings and the lambda 3, lambda 4, and lambda 5. Those are the quartic couplings that enter into the potential, and the masses are also three parameters, the masses of M2, M3, and so let's give some numbers. So like if you choose, let's say, the dark matter, the heavy right-handed neutrino to be of at this very high scale, 10 to the power 12 GeV, and if you choose this M theta, then you can get something. Then you can get a dark matter, let's say N1, which will be order of 500 kilo electron volt, which is determined by assuming that N1 saturates the relic density that we observe today, and we can invert this equation to get kind of number. So what is happening over here? So N2, which is shown by this yellow line. So this is the plot for the abundance and the time. So this is the time that has been rescaled in terms of temperature, and to get a dimensionless number, we define this variable z, which is nothing but the N2 by T. So as N2 decays, so this the number density of N2 falls down, but if this decay is simply violating, so it will produce very tiny amount of asymmetry in the baryon. Let's say this y delta b. So this, as this yellow line goes down, this asymmetry goes up, and it kind of saturates to this value, which has been measured by. So this gives rise to the generation of visible sector that we see.
So can you explain where you say this the symmetry over?
Okay, so the decay of N2 is a simply violating one. So it will introduce. So if you, let's say, if you have some number of N2 and it decays, it will give you very tiny amount of over values over anti-values. So as this N2 decays, the difference between the baryon and anti-baryon abundance starts to increase. So this green line increases, and this green line increases, and after most of the N2 has been depleted, this number density is kind of freezes in that we saw earlier, and it saturates the number that plant has observed, and this gives rise to the visible sector. And it will also produce eta, and this eta will dominantly decay, and so while during this decay of N2 it will produce eta, so this eta actually rises up very fast from here to here, and then it kind of decays, but this decay is kind of delayed due to the thermal scattering processes that it undergoes with the primordial law. So there is a competition between the decay of the eta, and there is a with the thermal scattering process.
So eta doesn't have like any mixing with the boson, or
so eta is a Z2 odd, so it will not have.
So lambda 3 is
I mean the zeroth component of eta and the zeroth component of his will not mix because the Z2 is intact. So they will not mix it. And there is no mixing between the mass eigenstate of H zero and theta zero. Because Z2 is odd. Because this theta is odd and this Z2 is intent. That's so this is done. This will not mix with the standard.
So eta doesn't have any other decay modes.
No, eta doesn't have any other decay modes. Eta cannot decay because eta going to H is not possible because the Z2 is contact. Eta can only decay into the electron and the if kinetics forms. So there are no other decay modes. But this eta, if you want to have a decay product of eta, you need to have some kind of dark sector particle in the kinetics. Otherwise, this Z2 will break. So because this is a Z2 odd particle, Z2 is conserved because you have chosen it. Okay.
To get that asymmetry, don't we need to assume some value of lambda 5?
So lambda 5. Okay. So lambda 5 is crucial to have a neutrino. So because this neutrino mass is directly proportional to the lambda 5, you need to have some coupling lambda 5 which which will give you the correct neutrino mass that will observe it, namely the neutrino oscillation parameters that has been experimentally been observed, and lambda 5 also appears in front of this coupling H eta whole square, so it will also take part into the scattering process. Eta will be change. So that will also be there, but that is not dominant kind of because lambda 3 is there, which will have a conversion that is eta H going to eta. So here I have shown the reaction densities that you can see that this scattering reaction density, that is this process eta bar going to HH, which is proportional to lambda 3, kind of dominates over this entire region before, let's say, around 300 or so. The scattering dominates, and this phi 2 goes dominantly into the primordial sector by this thermal scattering, and this kind of delays the decay of phi 2, and after some time this decay reaction density dominates over this scattering reaction density, and at a later point of time all of the phi 2 decays into N. So the N1 abundance increases, and then at some point of time it will all the phi 2 decays dominantly, and this N2 number is kind of freezes in by giving rise to this number, which if you invert you get a 500 kV scale pattern. So this is at a very high scale, and these numbers 10 to the power 12 and 10 to the power 10 GeV. These numbers are not accessible in colliders, but we have done this cogenesis at a very broad scale, which I will show you.
So N1 is the dark matter.
N1 is the stable matter.
Yeah, it's exactly with H, right? That's it. I mean, that means oh no, it's eta.
So lambda 3 and lambda 4 are the couplings with the hinge with the and N only impacts.
Yeah, I was trying to go for state. What are the connections with that metals and what directions?
Okay, so
How do you take this? That's right. They confuse with details.
okay. So it will go through, but it is suppressed. Because of this number, it is also suppressed, but you can have lower numbers to detections. So this is the reaction density, where most of the time is scattering turn dominates, thereby reducing the most of the etas into heats because of this they are in thermal contact with the primordial soup, and at some point of time at a later stage this decay reaction density kind of dominates over this scattering part, and then all the etas that are remaining they decay dominantly and produce this in one. So we have scanned over this parameter space to find out there are not only this point for which I have shown the result, but there are many points which satisfy all the bounds. Let's say it satisfies the neutrino oscillation parameters. That is, this region is actually allowed by experiments, and you get a dark matter which is let's say at the NV scale or let's say mostly at the scale scale. So this is a high scale cogenesis where the numbers are very high, But if you kind of tweak these numbers, you can also have sensible numbers which will give rise to an eminent dark matter candidate with this GeV scale.
This is MU. So I know some of MU.
This MU. So this MU is the
We have three masses, right?
so experiments do not observe three individual masses. So just to represent in this plot, I have taken the square root of those mass square. Just to make sure that this is the atmospheric mass scale, and this is the solar mass scale, and everything has to be in between. So this part is ruled out from neutrino oscillation data. This part is ruled out from cosmology, and this is so this part is ruled out by cosmology, and this part is ruled out by neutrino oscillation experiment. And for these plots, you have neutrinos that are not kind of meeting the experimental values.
Does this property hierarchy?
So I'm decided.
Whether it's a normal hierarchy or inverted hierarchy.
So we have done it for a normal hierarchy. We have not checked the inverted hierarchy, but this will this will remain most of these regions, but these can points will differ. So, but characteristically this will not change too much.
Really long list or
Lifetime. It's not too long lived, but it will have a late time decay. But just because it will have competition between the scattering processes and the decay products, and this is designed in such a way that the scattering rate is kind of dominant for most of the time, and then it decays. So it will live little bit longer, but not stable at the scale of. So it will eventually. It is not a stable. Okay. So this is a high scale, and this is
very problem in the nucleosynthesis or
no. So this is very before BBM. So this is very before BBM. So it will not have any kind of effect. So there is no problem. Okay. So and now if you tweak the numbers a little bit, you can eventually take this cogenesis scale to at around dB, and there also the same thing happens where this.
So this M2 and NM2
Yes, yes. So this is into an M2. I wrote it down, but in the images these are. Yes. So this M2 is the mass of the second atom that is heavy, and if you tweak the numbers a little bit, you can eventually arrive at this MEV scale dark matter candidate, where this cogenesis scale is around GeV, and here also for the most of the time the scattering dominates over decay, but at some point of time the decay reaction density increases it eventually beats the scattering, and all of the phi 2, all of the eta actually decays giving rise to stable dark matter candidate. And before this process happens, the CP violating decay of the N2 will give you the. Now you can also scan this. We have also done this scan, and most of this parameter space has been allowed by neutrino oscillation data. Also keeping in harmony with the Planck observed this sum over neutrino masses, and you also need to satisfy the observed relic abundance and the visible abundance that Planck has. So uh, in this cogenesis scenario, what we have done is that we have designed the decay and the scattering details in such a way that this model can accommodate both the leptogenesis and the genesis of dark matter simultaneously for a unique parameter space. And with this, I come to the conclusion.
You have to leptogenesis,
Mhm.
and then you have violating has.
So this is violagenesis via leptogenesis. So leptons are produced with a very small abundance, and then this abundance is kind of
Yeah, that's what we first doing leptogenesis and then we violating.
steron, and the steron factor is kind of
Okay.
this steron factor. I mean, this can have some non-trivial numbers, but it is around 0.3 because steron. If you look at the steron diagram, it will convert. Six fermions, six leptons into two baryons.
So your lepton asymmetry is of the same order of violence.
One.
Yeah, what?
So that is the conversion that takes place.
reason I asked is this, there are limits on the electron.
But that gets ultimately that gets converted.
Yeah, in your case it's not.
No,
That's the only thing.
that is a constant.
Yes. Because no, anyways, the limits are very big. 10 power minus 3 electron.
So, but electron asymmetry here we have.
Here, so here, your electron is effectively very different. Right, the factor of 3.
After.
Yeah, I think that the limits in sense of the cosmological limits, I think 10 power minus 3 or something.
The maximum value it can have.
Yes. This is very weak compared to oh, minus 3, minus 4. Some number. You can get from that CMD, BBM, CMD.
That's the cosmological upper bound for the electron asymmetry.
Yeah, so that, yes, correct.
Okay, that was the high and low scale part of this scotogenic model. With this, I come to the conclusion that this radiative neutrino model that is has been called is the scotogenic model, which is the vanilla scotogenic model introduced by Ernest Mach and provide solution to the not only the neutrino mass problem, but it can actually solve both these leptogenesis, both the generation of visible sector and the dark sector simultaneously. And this has been achieved by a interplay between this late time decay and thermal scattering of the dark sector particle eta, which is kind of heavy, and there is always a CP violating decay, which will eventually give rise to the visible sector by leptogenesis, and this will eventually give rise to a sub-GeV scale dark matter candidate at the KV or GeV scale. So this mechanism kind of is unique in the sense that there is an interplay which actually sets the mass of the stable dark matter. So that's all. Thank you. Thank you for it.
Thanks for the very nice.
Any upper limit on your dark matter mass?
Yes, yes.
So there is an yes. So
Is that there is a limit from us to give you a limit of anyone.
And you get some upper limit.
you have some upper limit, but you see the process that is actually happening is this Yukawa coupling. This Yukawa coupling sets the both the visible and the now stable dynamics proton that satisfies this Planck measure that is around 1 GeV, and if the mechanism is similar, then we expect dark matter mass to be at the 1 GeV.
So this is the same argument of accelerating arc.
Yes. So and now if you have 1 GeV dark matter, then you have the same this line will be similar to this red line will mark with this blue line. Now, if you have a little bit less massive dark matter, this abundance can be less. But if you have more massive dark matter, this abundance will be less. So, in a sense that it will have a lower and upper bound, but if it is governed by this same mechanism, it cannot differ too much because the governing Yukawa coupling is the same for generating the visible sector and the dark. And it also has to satisfy this neutrino and data and all those kind of things. But this can go on and on, but this will not go to a very high level because the production mechanism is kind of same for the visible and dark. You cannot tweak too much because the term that is responsible for generating the visible sector that is only giving rise to the dark sector because there is only one Yukawa. And no other channels or other processes for the production of N1. So the mechanism remains the same. It is more or less general to what happens in the physics.
So how do you actually detect? So like this kind of small and
Yes, so this is kind of hard. These numbers are pretty large. This can be detectable at colliders. At least, if you tweak these masses to be at GeV scale, you can have GeV scale eta, which you can detect in the colliders from this late time decay that you mentioned. But these numbers are large for colliders to detect at. But there are, I think strategies to search for this inner doublet from the left bound. I think this has a lower limit of around 80 GB, 80 or 100 GB. But this number can right now cannot be proven.
What is the diagram look like? The direct detection is it?
So this eta, if n1 is the dark matter, so this n1 do not have any kind of constant from the direct detection experiments because it is a freezing. It will not have any kind of diagram with the standard model except the neutrons. So it will negate the detection.
So you have some no, intensify if you are decaying carbon. It is whether the lifetime will be too long.
So no, the n1 is still. N1 is alive.
N1 has some yuga coupling. So through the p channel diagram with the eta as mediator, it can talk with electrons. So the N1 electron, there will be some direct detection channels, but the propagator is like the other is M3 or something like that for the high scale. The things are
That kind of evades this.
So it has coupling with something.
but N1 is also there.
N1 is electron.
N1 is
It will have
Electron coupling is there.
yeah, eta N1 electron coupling
is there.
that is the yuga.
That is the left search.
That is it.
But anyone can then decay to two electrons.
N1 is the lightest.
N1 is the lightest.
N1. So in that case, eta can decay to two electrons, right? So
Eta cannot decay to two electrons because electrons are standard model particles which are Z to even, and eta is a Z to odd.
Eta has coupling with electrons.
But eta has something with electrons on the other hand.
So the two particles, one is electron, other one is the
So N1 is absolutely safe. Just because this Z2 is from that, you cannot have decaying that. This is absolutely safe.
but also these yugas for N1s are very small.
Yes, so this N1 in cause are for this low scale cogenesis, this N1 in cause are of the order of I think 10 to the power minus 9 or
Yeah. So the direct detection will be
direct
less.
detection.
And this number M2 equals 150 in principle is just chosen randomly.
Yes. So these numbers are chosen randomly just to be so
Satisfy the neutral bound. To satisfy the neutral bound.
neutral bound is
Besides that, it's
regular.
Are there other questions? Okay, now let's thank Rohan for the next talk. Well, we are basically here visiting us for 2 weeks. Many of you must have read our papers very carefully. Yeah, she should be here.
Yeah, I'll be around. Very happy to chat. So yeah.
Thanks again.